This conference will now be recorded.
Very good morning, students. So as we promised, we will discuss today charging of a capacitor through CR circuit. Not only charging, we will be learning charging, discharging both. So let us start our discussion for today. This topic is very interesting and also important for competitive exam like JEE Mains, NEET, etc. So even in advance also some questions are coming from this particular topic. Basically the time constant, etc., which we'll be discussing today. All right, so let us start our discussions. So first of all, we'll discuss the charging of a capacitor. See, charging of a capacitor can be done simply connecting a capacitor with a battery. Okay, suppose, see, I'll be obviously discussing charging of a capacitor through CR circuit, but when there is no resistor, what is the situation and how is it different from the case when we just add one resistor in series with the capacitor? How things will change, that you will understand from here. So when a capacitor is simply connected to a battery through a switch, then what happens? Suppose initially this capacitor is uncharged. Now as soon as you close the switch, capacitor will charge in no time. So capacitor will charge, sorry, will get charged, or okay, capacitor gets charged, or I'll say get fully charged immediately. Okay, immediately. It will get charged immediately in no time. There will be no time lag. Okay, and see, suppose the capacity or capacitance is C for the capacitor, and the total charge which will be stored in the capacitor will be Q0 is equal to C into V. Okay, so this is the situation when there is no resistance. This is for a pure capacitor. For a pure capacitor, this is the case for a pure capacitor. Pure capacitor means capacitor does not associate with any resistance, or pure capacitor. Pure capacitor. Okay, now charging of a capacitor through CR circuit we will see. Okay, so in this case, see, if I draw the charge, okay, charge across the capacitor plate with time, how does it look? It looks like this. This Q0 is a constant charge, and it looks like, see, as soon as you switch on, in no time, t is equal to 0 itself, it becomes Q0. Okay, in no time it will be charged, and that charge will be continuing as the time elapses. Okay, so that's why you will get a curve, a curve which is parallel to the time axis. Okay, so this is the case when pure capacitor is being charged, connecting it with a battery, DC battery. Obviously here we are doing. All right, now we'll see charging of a capacitor through CR circuit. CR circuit. See, as soon as we add a resistor in series with capacitor, the situation gets changed totally. Now in this case also the capacitor will be charging, but charging will be very slow process. It will take very long time to charging will be very will be very slow process. Okay, it will take almost infinite time. That means very long time to get charged fully or with charge Q0. We'll just see that. We'll just derive a necessary equation. See what we are doing. We are just charging the capacitor, connecting a series resistor R, and obviously the capacitor has got capacitance C, and they are connected to a battery of potential difference V through a switch. So when the switch is closed like this, then what happens? The current will flow, right? Current will flow to the circuit. Initially there will be no voltage across this capacitor. Okay, there will be no voltage across capacitor, so initially the current will be maximum. Okay, and the whole voltage will drop across this resistor, and then slowly this gets charged by some dq charges. This gets charged by minus dq charge plus, so it will just increase or put on charges on the both plates, and then finally it will get charged. Okay, but if we see what is the charge at any intermediate time. So at any intermediate time, any instant of time, how the charge is, or how much is the charge, on the plates of the capacitor, how much the charge is. This is what we are going to see. So how to see that? So to find out charge at any instant of time, let me do one thing. Let me just close the circuit. Okay, so after closing the circuit, after some time t, let me just see, after some time what will happen, there will be some voltage across this, because suppose let me take let me okay, let us consider that the capacitor stores, let us consider after t time, this is separate thing, t time capacitor or charge on the capacitor is q. Okay, so how do you, like, how is it varying with time, that will see. So after time t, and say the current in the circuit is I. So by KVL, what you can write by KVL? I'm just taking the situation, current in the circuit is I, and Q is the charge stored across this capacitor. Okay, so by KVL, what we can write? We can write VC, that means voltage across capacitor plus voltage across this resistor, that has to be equal to this. So Q by C is the potential across C, because Q is the charge stored so far and C is the capacitance, and here it will be V is equal to IR. Okay, this is equal to V. V is the potential of the battery. Okay, so see, this I could be written as dq by dt, time rate of change of charge. That could be written as this. Okay, I could be written as dq by dt. So therefore, we'll just go to the next page. Okay, I have. Okay, I have to just derive it here itself. Let me just erase this part, and I'll get this. Or else let me get a page, new page over here. All right, so I have got extra page here. All right, so look, this equation I'll write here. So we have got q by c plus I into r. This is equal to v. V is the voltage of the battery, as you have seen in the circuit. See, dq dt, I could be written as dq dt. dq dt. If you can write that dq dt, let me write it here. So dq dt into r here plus q by c is equal to v. Okay, I can do one thing here. I can just multiply c everywhere. So c r dq dt plus q, okay, is equal to v here, right? So what I can do, I can just see, I can write, I have to integrate for charge q. Okay, so what I'm doing now, I'm doing, see, write q minus v with the minus sign here. Okay, and see, it will be, if I keep this way, so dq dt divided by cr it is. Okay, divided by cr. So I can just see, I'll be integrating for q. Okay, so this is, say, dt divided by cr. Okay, and here this particular term could come here, q minus v. Right now, if we integrate, see how I'm doing the integration. I'm taking the limit. See, q was 0 initially, and it has come to q. Okay, after some time. So this is q minus v again, and this is minus 1 over cr integration 0 to t into dt. So if we do the integration part here, look, this integration if we do here, so what will be that? Ln q minus v, okay, and this limit will be 0 to, with a minus sign over here. No, not minus sign. All right, so this is this with a minus sign t by cr. Okay, so this could be, say, now if I apply the limit here, so ln q minus v divided by minus v. Okay, because 0, lower limit 0, that also will come as ln. So I'm writing this, dividing this. Okay, so minus t by cr. All right, so see, we have to find out what is q. Okay, what is q? I think I have done a small mistake here. I had to multiply c everywhere, so here also one c will be there. So this is cv, this is cv, so this is cv, so this will be cv as well. I'll just rewrite here. This is CV, and here also CV divided by minus CV. Okay. Now I'll write, see, this CV divided by minus CV. This is equal to minus. I'm just taking anti-log both sides of the base of E. Okay. Now see this CV I'm taking as Q0. That is the initial that is the charge or the charge at steady state. Okay. Q0 is C into V, that is the final charge or steady state charge. I'm taking that steady state charge. Okay. So this part can be written as C Q minus Q0. Again, this is minus Q0 into e to the power minus T by CR. This part. Okay. So Q is equal to Q0 into 1 minus e to the power T by CR. So this is the formula we are getting at any instant of time. What will be the charge on the capacitor during charging? So at any instant of time, what will be the charge at any instant of time? What will be the charge on the capacitor during charging? See, I have written by KVL. I have written this, okay, and then I have just simplified for Q. Okay, so here you have to do some integration with respect to time, okay, and dq. So that we had just done. So what we have got, look, I can write here. See, the charge varies as Q is equal to Q0 whole into 1 minus T by CR. Okay. So this is the final charge. I'm sorry. This is the charge at any instant of time. At any instant of time. At any instant of time. Okay. So what you see in the beginning we had seen that it did not take long time to charge the capacitor. It was taking a very short time and almost immediately, right? But in this case, look, this equation, you can see this equation and see if I plot, see from here, Q is equal to Q0 whole into 1 minus e to the power minus T by CR. C and R has different meaning, I'll tell you. So you can see here how charge is exponentially growing. If I draw the charge at any instant of time, so it is actually exponentially growing. Charge is growing exponentially. Growing exponentially. Okay, charge is growing exponentially. Now, one thing we can see from here, see this term, only this term, if you see T by CI, this term if you see, so argument will be always argument of exponential will be always dimensionless quantity. So CR also has dimension of time. Okay, and it is actually denoted by tau. Okay, tau. So this is called, again, this is called time constant of the circuit. Time constant of the circuit. Constant of the circuit. CR circuit. So what is the expression for the time constant of the CR circuit? That is C into R. Okay. So what does this do? This has a very great role. This has a great role. it will actually determine how long it will take to charge the capacitor to its final value or to its steady state value. So this time constant will determine how fast the capacitor will get charged or gets discharged. So look what I'm trying to do. I'm just going to define one thing here. When at t is equal to 0, at t is equal to 0, what we get? Q is equal to Q0. No, not t is equal to 0. I take t at t is equal to at t is equal to tau. At t is equal to tau. When t is equal to tau, when t is equal to tau means t is equal to tau means t is equal to CR. Okay, this means CR. So when t is equal to tau, what happens to this equation is 1 minus 1 over E. 1 over E. Okay, 1 minus, I'm sorry. Sorry. So 1 minus 1 over E. Look at it. Look at this here. So at t is equal to tau, Q will be Q0 into 1 minus 1 over E. And this is nearly, or it is exactly, I can write the value. We can exactly write the value. I'm sorry. I'm facing some problem. Okay. So, I don't know. Okay, sorry. Let me rewrite it. This will be exactly equal to 0.632 into Q0. What does this mean? So what does this mean? Actually, this is how we define what is called time constant. Okay, we define time constant in this way. So how do we define time constant? We define time constant in this way, that when the charge of the capacitor becomes nearly 63% of the steady state value. Okay, better to define this in terms of current. Let me just go to current. See, current in the CR circuit, during charging. Obviously, let me just explain a little bit about this graph. See, this is the graph. This is the Q plotted in the y-axis, and this is the time. As you can see, at t is equal to CR, sorry, at t is equal to TC, here it is written as TC, the same as tau. Okay, so t is equal to t tau c, that is called time constant. At that particular value of time, the charge in the capacitor becomes 63% of its 63% of its steady state value. So 63% of this steady state value. Okay, 63% of steady state value. Q0 is steady state charge or the final charge in the capacitor. Okay, let me see here what is the current. See, we have got the charge at any instant of time is Q equal to Q0 into 1 minus T by CR. This is what we have seen. Now, if we want to get the current, see, I can just take the time derivative of it. So Q0 is a steady state value, so we cannot do any dQ0 by dt anyway. So this part we will integrate, minus sign will be there, and e to the power, see, this will be just plus e to the power t by CR, okay, along with 1 over CR, 1 over CR, okay, 1 over CR. So we look what we get, Q0 by CR into e to the power minus t by CR. So this is the current, and you look Q0 by CR, sorry, Q0 by C, this I can write as V, because initially, okay, fine, and so this I can write as V, because total charge by C, that I can write as V. V is the battery, voltage of the battery. The see, after fully getting charged, the voltage across the capacitor will be, across the capacitor plates will be the the voltage of the battery itself. So V. So Q0 by C, I have written V, and this is V by R. So this is multiplied with CR. See, this V by R, I can write as I0, initial current. I'll tell you why it is. Because see, initially, as I said, in the capacitor, initially there will be no charge. So the whole current will be flowing through the circuit. And since there will be no charge in this capacitor, so there will be no voltage drop across this. So the whole voltage drop will be across R. So that's why V by R, I can write as the current. This is the initial current. Initial I0 is initial current in the circuit, initial current in the circuit, that is actually Q0 by CR. Okay, I0 is equal to, all right. So how the current is varying? Current is actually exponentially decreasing. See, I have got, okay, let me so I hope you have understood this derivation. I am just erasing the derivation. I am writing just value of the current, expression of the current in the circuit, CR circuit while charging. So we see this. If we plot it, what we will get? This is T, and this is the current phase. See, the current is actually initially at t is equal to 0. See, according to this, at t is equal to 0. So I is equal to I0 at t is equal to 0. Okay. So I will be equal to 63 percentage. I'm sorry. This will be 73 percentage. Okay. Anyway, at t is equal to, okay, at t is equal to 0 itself, let us see first. At t is equal to 0, it will be the initial current, that is the maximum current, and then as much as you put value which are not equal to 0, so it will actually decrease. See how the current decreases? Current decreases like this. Exponentially it will decrease like this. Okay, so the current will decrease like this. This is the value I0, initial value. T is equal to 0 here. Okay, so initially in the circuit the current will be maximum, and then as soon as the capacitor gets some charge across this, so there will be some voltage drop across this, right? And you know what happens? This voltage across the capacitor will oppose the current flow. Okay, it will oppose the current flow. And when the capacitor is fully charged, that means when it is Q0 here, so it will be actually the voltage difference or potential difference across these plates will be V. So in the whole circuit there will be no potential difference, so current will be almost zero, but that will happen at after very long time. Okay, so this is the current. But how charge is varying? The charge is varying during charging, we have already seen, but still we will just draw once. See how charge is varying. Charge is varying like this. Okay, after a long time, actually we should draw. After a long time it will reach to its steady state value like this. This is steady state value. Okay, like this. So this is the charge. So Q0 is the steady state value, and this is Q. At any instant of time it varies exponentially, it grows exponentially. So charge grows exponentially and current decays exponentially. So this decays, current decays, and this grows exponentially. But both cases, see, to reach the maximum value and for this to reach the minimum value or zero value, it takes longer time, and that time depends on, see, that time depends on the time constant CR, tau c. Okay, this is tau c. So if the tau c is large, it will take large time to charge or discharge. Okay, it will take very long time if C and R both are very large. Okay, we'll just take up one simple example, but before that let me just draw one more figure here. Let me just clean this thing. Okay, let me show you all the variations. So this is Q. So Q actually grows exponentially like this. Okay, this is the steady state value Q0 with time. How the current is varying during charging the capacitor? So initially it will be maximum, then it will be decreasing like this. Okay, all right. So this is the maximum current I0, and this is I, and this is T. Okay, now what is the voltages across C and C, across C and across the resistor vary? Suppose VC across C and VR across resistor. See, we know VR is equal to I into R, I into R. So how I varies? I varies as I0 e to the power minus T by CR into R. So this will be V0 e to the power minus T by CR. That means initially the voltage across the resistor will be large. Okay. This is the time, this is the voltage here, voltage. So it decreases. Initially it will have maximum voltage across the resistor, and then just like current it will decay like this. Okay, or maybe it may be a little bit more faster like this. But how VC means what? VC means Q by C. Q by C. C is anyway constant. So how Q varies? Q varies as Q0 1 minus e to the power C minus T by CR. Okay, e to the power minus T by CR. So this varies as, see, this is actually growing, isn't it? This is growing, exponentially growing. There will be Q by C0 here. C. So this is VC0, or let us take this as like this itself. So Q by C0. So initially how much it is? T is equal to 0. So T is equal to 0 means initially it is 0. So initially it is 0, it starts from here, and then it reaches to maximum value. So how it varies like this. Okay, so this is actually VC, and this is VR. Okay, this is VC. See how they are varying. They are varying. So VC is varying, like it is growing, exponentially growing. Sorry. Exponentially growing, exponentially growing, but this is exponentially decaying. Okay, so this is how the voltage across capacitor and the resistor varies. Okay, and you know, like when the capacitor is fully charged, the whole voltage is becoming V. Actually, whole voltage, this is not V0, this is V, say this is V. So V is the battery voltage, right? V is the battery voltage at steady state of the capacitor. When it is fully charged, voltage across this will be V, capacitor will be V. Okay, at this point it is V, and initially the total voltage will be across VR, that will be actually equal to the battery voltage. All right. Okay, I have got two examples. So far we have discussed the charging part, we have discharging part also. Similarly, we'll discuss that. So look here, a capacitor of capacitance 1000 microfarad. So 1000, that means 10 to the power 3 microfarad. Okay, if we require, we will convert it to farad also. Connected to a resistor of resistance 150 kilo ohm. Okay, now a battery is connected, and a battery is 1.5 volt. Find the maximum current that flows through the resistor during charging. So when the current will be maximum, see at t is equal to 0. Okay, at t is equal to 0, the current will be maximum. And what will be the expression for the current? First of all, what is the expression for the current? At t is equal to 0, what is the current? See, current is here, here, I0. At t is equal to 0, current will be I0, isn't it? Expression for the current was this: I0 e to the power t by c. So at t is equal to 0, the maximum current will be there. Question is, the maximum current flows through the circuit. So maximum current is actually I0, that we have seen V by R. What is V? The steady state charge Q0, or see, this is the voltage of the battery. We don't have to go anywhere else. So this is the voltage of the battery. V is the voltage of the battery. Voltage of the battery. There is a 1.5 volt given. So 1.5 volt. Okay. Now R is how much? R is 150 into 10 to the power 3 ohm. Okay, so you can find this out. So This is 15, 15, so I can get 1 into 10 to the power 10 to the power minus 5, or we can say 0.1 micro ampere. So this will be the current in the circuit initially, 0.1 microampere. Now we'll go to the next problem. See, an uncharged capacitor and a resistor are connected in series. As you see, capacitor and resistor are connected in series as shown in the figure. Figure is this one itself. Battery voltage is given as E is equal to 12 volt and C is 8 microfarad and this is 500 kilo ohm. So you have to find out one by one what is time constant. Time constant tau for the circuit is C into R. So what is R? 50 kilo ohm. Sorry, 500 kilo ohm into 10 to the power 3 ohm. And what is C? C is 8 microfarad. 8 into 10 to the power minus 6 farad. So this will give you second because it has got unit of time. So 3 to 5, this will be 40 along with 5. Okay, so 10 to the power 3 into 10 to the power here 10 to the power minus 6. Okay, this is 10 to the power 5. Anyway, so you will get second 4 second actually. So this will be 4 second. Okay, so the answer is 4 second CR. Okay, now we have to find out what is the maximum charge on the capacitor. So what is the maximum charge on the capacitor? Q0, that is CV, that is the total voltage into C. C is 8 microfarad 10 to the power minus 6 and this is 12 volt. So how much? So it will be 96 into 10 to the power minus 6 coulomb. This will be actually 96 microcoulomb. Sorry, yes, microcoulomb mu C. So this will be 96 microcoulomb. So these two parts are over. Now the last part is the charge on the capacitor after capacitor C second after the switch is closed. So at any instant of time we have to find out. Okay, so we know charge, we have to find out here what is the charge on the capacitor after 6 seconds. So that means this small t is actually 6. So we have to find out Q is equal to Q0 into 1 minus e to the power t by CR. So here CR is 4 seconds, t is given as 6 seconds. Okay, Q0 we have found out already 96 microcoulomb. Now what is the charge after this? So Q we have to find out. So 96 into 10 to the power minus 6 coulomb into, this is dimensionless anyway, so this whole thing will be in coulomb itself. So 1 minus e to the power 6 by CR is 4, so this is 96 into 10 to the power minus 6, 1 minus 3 by 2 or 1.5, or we can write this as 96 into 10 to the power minus 6 whole into 1 over 2 by 3. No, this is 3 by 2 itself, because minus is there. I can just write that like this. Okay, so this is the value. Now you have to just do a little bit of calculation here, and obviously what you get is 74.5 microcoulomb. This you will get as the answer. Okay, now we'll go to the next part, discharging. See, when you discharge the capacitor without any resistor, see, as soon as you close it, so discharge of capacitor without R takes no time, actually takes no time. That means as soon as you close it, see, initially what happens, it has a lack of, see, lack of, this has lack of electron, this has excess of electron. As you connect it, the excess electron just go to the positive plates, that's all, and they will actually get neutralized. So it takes no time, it will be immediately done. Okay, all right. So now discharging, but when discharging happens to the resistor, this will take longer time. As we have seen, this will be again an exponential phenomena. Okay, so exponential phenomena, how we can see from here. So similarly, here also by KVL we can write KVL by KVL. See here, initially it is fully charged, so we know Q0 by C. Okay, or at any instant of time I am writing, so I will just write Q by C itself. This is IR. That is equal to 0 because battery is not connected to it now. So here similarly we'll write dq by dt, sorry, dq by dt into R, as we had done previously here with R. Q by C is equal to 0. So what I need to do, see, I can write dq minus q by CR, right? So dq by dt, I can just bring this dq by q here, keeping this dt by CR here, and just do the integration. So integration, initially it was q0, okay, finally it will be 0, and here t is equal to 0 to t. So this is the limit we need to take. In fact, what I'm trying to do, at any instant of time, I'm not taking infinity. If I take t is equal to infinity, then it will be obviously 0 here. Charge will be 0. But I'm not taking infinite, I'm taking any intermediate time. So this will be q, say. So now if you just do the integration part, so what it is, see, it will be ln q by q0, and this side it will be minus t by CR. So from here, if I just write it in terms of antilog, see, I just don't want logarithm. So q by q0 is equal to minus e to the power t by CR, or q0 is equal to, sorry, q at any instant of time, how it varies, q0 into e to the power t by CR. So this is how it varies. So how the charge is varying? Charge is varying as q, see, exponentially. It is q is equal to q0 e to the power t by CR will be there. This is CR. Obviously, this rate of this decay or discharging depends on the CR value, that you know that. So see here, when t is equal to tau or tau c, whatever you say, q becomes at this Q becomes Q is equal to Q0 by E. Q0 by E, and that actually is nearly 37% of Q0. 37% of Q0. That means what? Time constant is the time taken by the circuit to discharge the charge of the capacitor by 37% of its maximum charge. That is actually the time constant. Okay. Similarly, so we have got expression for the, see, we have got the expression for charge. Okay, so see, at t is equal to, so the charge will be, maximum charge will be decay to 37%, almost 37%. Okay, and see, current, if I just take the derivative, I'll get minus sign over here, Q0 by CR. E to the power minus T by CR. So this particular part I'll take as I0. Minus I0 e to the power minus T by CR. So what does this negative sign signify? This signifies that the current in the CR circuit in the CR circuit, this signifies that the current in the CR circuit is in the opposite direction, is in the opposite direction. In the opposite direction. Okay, so current will flow. So if I draw the voltages here, see VC how it varies. VC will be maximum in the beginning, then it decays like this. This is VC, voltage across the capacitor. What about voltage across the resistor? VR will be with a minus sign. See here, I0R e to the power minus T by CR. Or this is okay. So look, if I plot, so I0 and V0 is actually V initially. So initially it has, say, minus V. So this is how it varies actually. Okay, voltage across a resistor. Okay. So sometime in your exam there will be a question, instantaneous phenomena with capacitor. Instantaneous phenomena. After closing the battery, okay, instantaneous phenomena. Okay, so instantaneous phenomena means as soon as you switch on the battery of the circuit, what happens to this? What happens to the current in the circuit? So current will be maximum initially. Okay, current will be maximum initially. Instantaneous phenomena. After a long time, what happens? See, it got charged. Okay, charged. So it will oppose the current flow in the circuit. After a long time. After a long time. After a long time, so the voltage drop across the capacitor plate will be same as the battery source. So after a long time, I current in the circuit will be zero. Current in the circuit will be zero. Current in the so I0 so after long time I0 I is equal to 0 is the current in the circuit. So after long time behavior of capacitor as insulator. Long time behavior is as insulator. And short time behavior or instantaneous behavior like conductor. Okay, so today we'll stop it here. In the next class, we'll take up various numerical example on this, and also we'll go with LC oscillation. LC oscillation. Next class we'll see LC oscillation. LC oscillation. Or okay, no, this we'll discuss in the AC part. That will be better. We'll take up in the next class numerical example again during the related to charging of capacitor, long time, short time behavior, etc. So next day will be numerical problems. Okay, so thank you for your patience. Bye for today.